All right. Well, thanks for having me. Since I was already introduced, well, anyway, hello everyone. I should look like that guy, sort of, and my handle on the intertubes is that one. Today we're going to dive a little bit deep into what libuv does. Who here sort of knows about libuv already? It exists? OK. How many of you figured it out because you saw a backtrace and an assert? A few. And how many suffered the real path thing in V6? Not so many. OK. So let's try to understand this a little bit better, which is the plan. For those who are not familiar with libuv, it's our cross-platform I/O library that, as Dr. Brian said, was kind of brought in to fix Node on Windows, let's say. So it can do asynchronous I/O, but also more things. So there's more to just doing sockets on Mac OS and Linux and FreeBSD and Windows. You also need threading primitives, mutexes, what have you. It's relatively small. It's 30,000 lines of code, sans the tests, which seems like a lot, but as Miles just said, you don't need to understand everything. And that's sort of the message I want to convey today. We're going to start at the top and start digging down until we sort of understand what we want to understand. And if we want to go deeper, we can go deeper. But we don't need to necessarily do it. It's used by Node and many other projects. One that I'm particularly happy about, knowing that it uses libuv, is MAME, the emulator. They started using it recently, and I'm pretty happy about that. So what features do we have? We are an event loop that can do TCP connections, can do UDP, can do your TTIs and your pipes, processes, signals, file system, APIs. And we do that with a consistent cross-platform API, and in a way that sort of you don't have to think about it. The idea is we take care of the shit, so you don't have to. So architecture-wise, I think there are three pillars to libuv. The first one is the loop itself. So there's a UV loop type, and this is our sort of context. So that's where things happen. And when we say libuv is an event loop, it's a single-threaded event loop. So we run one loop in one thread. If you want to run more loops, you typically run them in different threads, because the moment you start running the loop, that thread is, well, busy at the moment. Then we have handles. A handle is a resource, which is an entity that is able to do certain type of work. As in, we have timers, for example, which are a type of handle. And this handle basically calls a callback after a certain amount of time. We also have TCP handles that will handle your connections, so you're reading and you're writing over the connection. This is the job of this resource. And requests are operations. So over a handle, or in a standalone way without a handle, we can perform an operation. UVIOT is a request to write some data over a stream connection, and that is a request. Now, we also have UVFS open, for example, which uses a file system request to open a file. But UVFS open is a standalone request. It doesn't use a handle. And UVIOT uses the stream handle where the operation is actually happening. And we also have other miscellaneous utilities, let's say. So as in blocks, let's say, we have, I would say, three main blocks that are operating system dependent. We have our network I/O, our file I/O, and some other stuff. And then we have other things that are operating system independent. Some of the things that are operating system independent are technically not independent, but they become independent because they are built on top of the other stuff in the third box. So let's now zoom in to each of these ones. So when it comes to network I/O, let's say, and allow me to put some things that are not strictly networking here as well. At the API surface, or what Node uses, what your application might use, is the blue boxes. So we got our TCP handles, our UDP handles, our POL handles to do low-level I/O. So that is what we use, right? So now let's see how those are implemented. So TCP pipes and TTIs are all stream-based. It's a stream of data. So there's a common sort of parent class to them, let's say. libuv internally is architected in this way a little bit. You could say it has a simple object model, which is UV stream T. That means that if you want to understand how a TCP handle works, let's say you say, well, OK, I'll just open up the source code and see what happens. The first branch you see is I open the source directory, and now I have Windows and Unix. So for the purpose of this talk, we're going to look a little bit towards the Unix side, but I'm going to explain why. So we're on the Unix side, and we're like, OK, so there's tcp.c, so that's a good place to start for understanding TCP. Now, once you go through that, you'll realize that half of it is not there. So why? Because actually, writing on a TCP handle or a pipe or a TTI is the exact same thing. So all that is part of stream.c, because that's where the stream common functionality is. So if we start trying to understand what the TCP handle does, we would go through that, and then we would jump towards the stream. And the good thing is that once we know how the stream works, we actually know 80% of how pipes and TTI handles work as well, as a bonus, let's say. Now, both streams plus UDP plus the poll handles, they perform certain I/O over a file descriptor. And on Unix, we have an internal thing called UVIOT, which abstracts this. This is basically one layer before epoll, KQ, and friends. So what this means is that if you read all the way up to UVIOT, you can get a perfect grasp of what's going on in libuv without necessarily knowing how we call epoll. For it's like a black box of something that looks like select or poll, and it calls some callback when a socket is ready for reading or for writing, and that's it. Now, do you want to know more? Fine, no problem. You want to know more about epoll? Well, the Linux bits are in a file called linuxcore.c. The macOS files are in a file called darwin.c, and so on. So every bit and piece of operating system-specific stuff is in a different place. So you can always sort of zoom into the places you want and leave the other bits out, because they would only add sort of noise when you're trying to explore how a particular subsystem works. And the reason why I mentioned we would focus a little bit on Unix side is because on Windows, for example, it's not the same thing, as in TCP pipes and TTIs don't behave the same way internally on Windows. So we shim that, we make it look like that. But it's sort of like the 10-meter rule. If you get closer than 10 meters, you'll see the skeletons in the closet. And there is no UVIOT because they don't share a common ancestor. So that doesn't exist. So on Unix, you have more layers of abstraction, so you can stop at different levels and continue exploring should you want to. Now let's look at file I/O. So file I/O is typically UVFS requests. Now I added some others here, like UVWorkT, which is user-supplied functions to do certain work, custom work, and getIDinfo and getNameInfo, which are the DNS requests, let's say name resolution. So all these, they run on a thread pool. And this thread pool is built with our operating system independent utilities, or abstracting utilities, which means that the thread pool itself is shared between Windows and Unix, and is not operating system specific anymore. And now let's have a word on threads, because everyone thinks they are bad and whatever. We use a few of them. There is a thread pool. Yes, there is one. And there we only run the file I/O requests. Now, there's that very nice blog post about why nothing else works properly. It was written 4 years ago, but to the best of my knowledge, that is still the case. Every so often, the discussion will pop up why some other mechanism is not used. But so far, we haven't found a better one. So we use a thread pool for all file requests on every platform. So please interiorize that we don't use it for network I/O. If you were at Node Interactive, you might have heard Bert kind of complaining that the internet is wrong, and there's many incorrect diagrams about what Node does. So if you see something, say something. You see a broken diagram with event queues and worker threads and the reactor pattern. Yeah, we follow that, but it's not implemented that way. So please verify this. This information is sort of important to get people on the same page. Now, I said there is other things in the libuv toolkit, let's say. We got timers, we got this thing called loop watchers that run at different points in the event loop iteration. All these are, at the moment in master, they are all like common for Unix and Windows, which is a good thing. On V1X, they are separate implementations, so we saved some code there, so they are now completely independent. And in the dependent section, we have, well, signals, child processes, and other utilities. So let's look at how the event loop actually runs at the libuv level. So the idea, even in the name, we have event loop, so there must be something that repeats itself. So what we first need to figure out is, do we actually have to do any work? Is the loop, we call this the loop being alive. So if the loop is alive, we do work. If it's not alive, we don't do any work. Now, if it is alive, then, OK, let's update the time. So we have this concept of when now is, and when we use this to know when timers need to run. Then we run the timers if they are due. Then we run pending callbacks. Pending callbacks are callbacks from previous operations that have completed. For example, when you want to write on a TCP handle, you do a write operation, and the operation is performed, and then the callback with the result comes back at you. This is the moment in time when it comes back at you. Then we run idle handles, which are very poorly named because they don't run when nothing is idle. They run all the time. And they have an interesting property, which we'll see in a bit. Then we run prepare handles. Prepare handles are, by definition, always running before blocking for I/O. Then we block for I/O, and I/O happens after certain outside the stimulus happens. So all your new connection callbacks, your data read callbacks happen at this point in time. And kind of in an analogous way to check, we run prepare, which runs but after the polling phase. And last, we run the close handles. So when you UV close a handle to sort of dispose it, once we're done with it, we call the close callback. That will be at this point. And now let's see how the C code for UV run, so the heart of the event loop, translates into this. I thought this was going to be very low level, but then Francisca showed some assembly, so then why not? So now if we look at this, and I think it should be big enough to read, I just trimmed one comment, and the first three integers, put them in a single line so they would fit better. If you look at it sort of chunk by chunk, you'll see that translates perfectly into the block diagram that we have seen just now. So first we figure out if the loop is alive, whatever that means. Then we start doing work because we assume that it is alive. We update the time. We run the timers. We run the pending requests. We run our idles, the prepare, we computed the timeout for how long we're going to block for I/O. We block for I/O. We run check. We run the closing handles. Some other stuff that if you see the comment that I scraped there, it makes sense. And we start all over again. So my point here is that I realized while preparing this talk that this is a very good entry point, because you start at the heart of the event loop. What runs? What happens in an iteration? Well, this happens. And it turns out that the diagram and the code are kind of the same thing. And then we can zoom in to each of these functions and see what they do. So let's look at a few of them. So what do we say? What does it mean for the loop to be alive? Well, if there's any active handle or active request, or if there's any closing handle, we consider it to be alive. And even if C is not a language you are very familiar with, that thing reads pretty much like English. So the idea is that there's many tiny pieces you can zoom into and understand them independently, or you can forget about it and say, well, this function promises to tell me that the loop is alive. Fine, I'll believe you, and move on. Like right there, you see UV has active handles. How do we know that? Well, trust me, we know. Or you can zoom in and see it. Let's look at how do we check the backend timeout. This is more interesting. So actually, if you look at the code right now, it's not like this, because while I was preparing this talk, it was longer. But I realized that it could be shortened, so I sent a pull request. So for how long should we block for I/O? Well, if the loop is about to stop, first thing there, well, there's nothing for us to do. So we block for 0 seconds because we're about to finish. If the loop is not alive, it means we're about to finish as well. So we block for 0 seconds. Now, the third one is more interesting. If there's any idle handle, which is in that queue, those are the ones that are active, we block for 0 seconds. This is a property of idle handles, which prevent the loop for blocking for I/O while they are active. Then if there's any closing handles, we also don't block, because remember where we are in the diagram. Closing handles will run later. So if we block for 1,000,000 years, then those closing handles will never be closed. So then we block for 0 seconds so that we can run those callbacks later. And otherwise, we calculate the next timeout. Now, I can tell you what the next timeout is, which is, it depends. If there are timers, it will be the closest timer. If there are no timers, infinity. So the thing is, we started by saying how the loop runs, then we know how to compute the backend timeout, and now we could zoom into how the next timer is computed. We break things into small pieces, and we can look at them one by one. Let's look at the next one. How do we run timers? Well, timers in libuv at the moment are implemented as a min heap data structure, which means we access them by the closest due timer first. So what we basically do is iterate through our heap of timers and check which ones are due. And because they are sorted by due time, the moment we find one timer which is due later than our idea of now, it means that the rest are the same. So we break off that loop, and we don't need to do anything. Otherwise, we run the timer callback, and we're done. So that's how our timers work. Now, let's look at how this translates into what you can see in a Node application. So remember this diagram. Try to remember it photographically, let's say, in a second. And there we go. So we got timers, but in Node as well, right? But in Node, one Node timer is not one libuv timer, because I understand that that would put too much strain on the garbage collector, so they are coalesced. So if two timers are due at the same time, they are backed by a single libuv timer. Then there are pending callbacks for all sorts of operations. We saw it on the other diagram too. We poll for I/O all your data events, all your new connection callbacks will be called here. And then we got set immediate. So all your set immediate callbacks are called in a check handle. And if we remember the diagram, checked handles run after blocking for I/O. And we use an idle handle to also prevent the loop from blocking if there is any set immediate thing pending there. Now, the question of the $64,000 is, when do the process next tick run? Those callbacks run? Well, they run in a function called make callback, internal to Node, which is called when you cross the boundary between C++ and JavaScript. So when the C++ side got a callback from libuv, for example, and you want to call into JavaScript, into a user callback, at that point, some of the next tick callbacks will run. So set immediate is not immediate, and next tick doesn't run in the next tick. What are you going to do? So all this follows what I call the onion architecture, which is layers upon layers of abstractions, and the deeper you dig, the more you cry. So you got your net socket, which is what you work with. If you peel that layer, you see the TCP wrap, which is written in C++, which then uses a UVTCP handle, which is in C, and then at some point in time, we really talk to the operating system. So the idea is you can start at the top and start digging into how things work to get a better grasp. And now that we know, let me give you a status update into what's up, what's the state of the union in libuv. So we are currently actively developing the V1X branch. And as I said that V1.10 was imminent at Node Interactive, so it's now more imminent. It will be enterprise ready, as in we have AIX and ZOS support. I doubt there's many pieces of software supporting those things in the current software world. We got a new release champion for this release. We'll be calling from Nearform. This will help us reduce the buzz factor. I have been doing releases since 1.0, and now he'll be doing this one. So that's great. We have 12 new APIs since 1.0, and the ABI remained stable. So this was what we promised we would do, and somehow we managed to keep it up. So I'm really happy that things kind of panned out as we planned, because we have seen the Node story before, right? And we actually kind of parted ways with Joyent long before Node did and released 1.0, and we made these promises, and we're still keeping them. So it's, I guess, a good idea that the project is healthy, good impression that the project is healthy. We have 7 maintainers at the moment, 5 are active, but the rest of the people remain involved, so we can always back them with questions. In master, we have 2,000 lines of less garbage, which is always a good thing to have less to maintain. This came from removing Windows XP support and burning it with fire. So that is happening, and whenever V2 happens, well, XP support is dead. Node killed it, we are killing it next. We clean up the platforms, as I said, also old Mac OS. There's a number of open pull requests. I'm sorry if one of them is yours. We'll work through them, is the idea. We tried to lay up some groundwork because, well, nothing gets you more in the mood than deleting 1,000 lines and code that you don't have to maintain. And we can even improve the code now that we have removed all that craft. So what are the plans for libuv v2? We're fortunate enough to 4 of the maintainers, we gathered together at Node Interactive and bounced some ideas also with members of the community. And then they are up on SlideShare, so you can check those out. Basically, I want to improve the documentation. There's this libuv book. We plan to take that over, and the author is cool with it, which is brilliant. And make it current and integrated with our current documentation. Improve the thread pool, so instead of having a fixed number, has like it scales automatically. We have a number of improvements for timers and reading data from handles with 2 new requests. And another interesting thing, which would be a companion library to libuv extras. And one of the things that Node might be interested in is UV seriality. This is sort of on the air, but actually Miles put out a project for the Node Outreachy program, and there is a student who applied for it. So we'll be working with her so that hopefully this actually works. We inaugurate libuv extras with a working serial implementation, and then at some point kind of finds its way up to Node, and everyone's happy. So this will be our sort of incubating place for new stuff to experiment with and see what happens. We'll also have an OpenSSL-backed handle, which Fedor already wrote. The idea is that it lands there. So that's what's new for V2. If you want to reach out to us, that's the website and where the API documentation is. IRC channel, libuv Google group for questions, and I tend to keep an eye on Stack Overflow as well, every so often. But, well, you know, I also wanted to give a shout out to all our maintainers, the co-maintainers, and the collaborators of libuv. So we got Ben, Bert, Colin, Fedor, Santiago, and Imran. And myself, we are the people sort of trying to get the thing going with many patches from the community. So if you submitted an issue, a patch, thank you very much. If you have any questions, find me around. Unfortunately, I won't be here after lunch. I'm leaving, and I'm very thankful for Nearform. They work with me in sort of getting my schedule right, because day after tomorrow, I'm speaking in Buenos Aires, and today I'm here. I'm really happy that everything worked out. And, well, there is this thing I made for sort of the community, is a libuv keychain, laser cut. I have a bunch of them, so find me out if you want one. Thank you very much.